Hi. So today I'm going to talk about for example, related changes or related rates of change. It's like, okay, this example here. Okay, this comes from a book. Of course, this is not my picture. I didn't take this photograph or anything. So somebody throws a pebble onto a lake, onto a calm lake in a perfect, this is theoretical stuff. Okay, they throw it perfectly vertically and the lake doesn't have any other disturbances. So you have these concentric rings here, which are the waves, right? Well, what it's saying is that, what the exercise is asking for is, first it informs you that the radius is increasing at about one, let me read the exercise here. Is increasing at a constant rate of 1 foot per second. Okay, so you know that the radius in terms of second is changing at 1 foot per second. So when you throw the pebble, there's nothing. 1 second later, the outer ring, the outermost ring has 1 foot of radius. On the second, this outer ring is already having 2 feet of radius. In the third second, it has 3 feet of radius. Okay. So what do you have? You have at a rate here, the radius is changing with respect to time. So you have dr dt, and this t, okay, of 1 foot per second. Okay. And it's saying that, it's asking when the radius is 4, at what rate is the area going to change? And you go like, okay, this is kind of weird. What do you mean by that? Well, so the exercise wants the rate of change of the area per second. So what it wants is dA, A means the area, per second, so it has to be dA dt. That's what it wants. Okay. This is a little bit hard to visualize, but think about this for a second. When the radius is 1, what is the formula of the area with respect to the radius of a circle? Okay, so area equals pi r squared. That's the area of a circle. Now, when r is 1, what are you going to have? Pi r squared. So it's pi 1 squared, which is just pi. So the area is pi. And the radius is 2. The area is going to be 4 pi. And the radius is 3. The area is going to be 9 pi. I'm just going to do one more. And the radius is 4. The area will be 16 pi. Okay? Now, I'm going to get a calculator here. I'm going to open a calculator. Okay, it's open. I don't think you guys can see it, but it's open. So when going back here, when the radius goes from 0 to 1, okay, you got a 0 here. 0, the area is 0. So when the radius goes from 0 to 1, you just increase 1 unit, okay? And what do you have? Well, pi minus 0 is just going to be pi. So first, the change is pi. And pi is kind of like 3.1415, blah, blah, blah. But it's 3.14, okay? So this is the difference from R1 minus R0. Okay. Now, when the radius changes from 1 to 2, what do you have? Well, you see, it's a little bit hard to explain, but it's going to be like 4 pi minus pi, that's 3 pi. So it's going to be 3 pi here. I'm just going to write 3 pi. Okay, that is the change when the radius is 2 to when the radius is 1. Okay, so it's going to be the change when the radius is 2 minus radius 1. So you see, from 0 to 1, the radius increased just 1 foot, and from 1 to 2, it also increased just 1 foot. But you see that as it goes, the change in the area is going to get much larger, okay? From the radius 3 to the radius 2, what do you have from 3 to 2? Well, 9 pi minus 4 pi, you got 5 pi. Okay, so the radius, the rate of change of the radius with respect to time is constant. It's just 1 foot per second. But the rate of change of the area is not constant. Okay, first the change of the area was like from 1 unit of foot in the radius to the next was just pi. And then it became 3 pi, and then it became 7 pi. And you see here from 16 pi minus 9 pi, well, 135. And then from 16 pi to 9 pi, you're going to be 7 pi now. So you see that the rate of change in the area is just increasing more and more and more. Okay, so what he's asking is, when the radius is 4, what's going to be the rate of change in the area with respect to time? Because the rate of change in the area is related to the rate of change in the radius, but it's not the same. Because the rate of change in the radius is constant, it's just 1 foot per second. And the rate of change in the area is increasing, okay? It's increasing more and more and more. So what you want is to, how are you going to solve this thing? Okay. So I just did all this to give you the concept, because you see, calculus is not just about memorizing formulas and how to solve exercises. It's about interpreting the exercise. You got to know what the heck you're doing. Okay. So here you have a rate of change that you're informed. You have this. Okay, this is what you have, and this is what you want. Man, this is what you want. Okay, and this is the point that you want this change right here. So, and there's something else too. So you have a change in the area, which is what you want, and a change in the radius. So since you have these two changes, you need a formula that relates the area with the radius, not the change in the area to the change in the radius, but the area in the radius. And here you have it right here. So area equals pi r squared. Okay. So what you want to do is you want dA dt, right? So you're going to use this formula here, and you're going to differentiate everything with respect to time. So you have dA with respect to time, which is what you want. Okay, pi is just a constant no matter what, so never mind that. Okay, and then you got to differentiate this stuff in here with respect to t. But here you got a problem. You don't have a t here. So remember, this is implicit differentiation, and it's the chain rule altogether. Okay, so you gotta differentiate this stuff with respect to r, and then you differentiate r with respect to t. So what you're gonna do is dr squared with respect to r, and then multiply by dr dt. If you cut these two, you're gonna have exactly what you want. Dr squared with respect to dt. Why did I leave the pi behind? I could have put the pi here, but it doesn't matter because it's a constant. So you just keep it out. Okay, you just keep it out. So doing this thing here, I'm gonna do it directly because I already showed you guys differentiation. So it's just gonna be 2r dr dt. This is implicit differentiation with the chain rule. Okay, so do you have dr dt? Yes, you do. It's 1. Okay, so this becomes 1. Forget about it. And you have, so dA, you know that dA dt equals 2 pi r. Okay, and you want, when do you want the rate of change of the area? When r is 8, when r is 4. So you're going to replace this r here with 4, and you got 2 times 4, it's going to be 8 pi. Okay, so what does that mean? It means that when the radius is 4, the rate of change, this is going to be the rate of change of the area with respect to time when r is 4. Okay, but when r is not 4, is it always going to be 8 pi? No. When r is 3, it's going to be a different number. It's going to be 6 pi. right? Because all you got to do is to replace the 3 in here. When r is 2, it's going to be 4 pi. So you see that the rate of change in the area is increasing. And this makes a lot of sense. This makes a lot of sense. Visually, I just want to show you guys something here. Visually, let's do this. Okay, you got this. Now you have something here. Let me see here. Yeah, I think it's good. And now you have something here. See here. I'm just trying to show this visually to you guys. I'm trying to make it as perfect as I can here. Yeah. And now just one more. Oh, hold on. For the next exercises, I'm just going to use the concepts, okay? I'm not going to be so slow like this. Okay, so I'm just going to paint the stuff with, I don't know, maybe red. So you see, the distance between this one is the same as the distance between this one and the same as the distance, kinda. Okay, it's not perfect, but it's kind of the same distance between this one. So it's just 1 foot. But you can see that in here, from this circle to this circle, what do you have? You have this area here. Now let's talk about the second to outermost circle to the outermost circle, from this one to this one. Look at this entire area in here. Look at this stuff. I'm going to do this. I'm just going to paint it just a little bit. I want you guys to understand how this is solved, the concept, and visualize this stuff. Okay, so what is the largest area? You can see that this area right here is a lot larger than this other area right here, okay? This one is small and this one here is large. The red one is large, and the one pointed out by the orange area is smaller. So you can see that the feet, the rate of change of the radius with respect to time was the same, okay? You have all these concentric rings in there, and well, their outlines, the difference between one outline and the other is just the same distance as any other outline to the next one, okay? But the area is increasing a lot larger. So yeah, it's increasing a lot more. Try to imagine when you have something like this, okay? When you have something like this, and then you got another ring, a lot larger, like something like that, okay? When you have this, the difference is going to be this entire area here. This whole thing here, look at the size of this stuff, and compared to the size of this, okay, you can see that the rate of change in the area is increasing a lot more. So this is just to visualize. I know it's kind of a pain in the ass. A lot of you guys that are good at mathematics are going to say, of course, yes, I can visualize, stop the video. But it's just because it's the first time that we're dealing with this. Okay, so I'm always going to refer back to this exercise, the exercise of the pebble on the lake, or in the lake, being thrown at the lake, whatever you want to call it, just to make sure that you guys see, visualize, and because visualizing is very important. You have to not know all the mathematics in your head, but you got to visualize the thing, got to be able to see it happening, so you have some kind of intuition of what to do and what to expect. Okay guys, that's it.